Hey Calculus, today we are going to start learning how to take antiderivatives without going backwards in our head. Antiderivatives are also known as indefinite integrals. That's the fancy calculus name for it. Let's review the notation. The notation includes the elongated s in the front of the function and dx after the function. When those two things are around the function, that's the notation telling us to take the antiderivative. The actual function, the name for that in the calculus world, is called the integrand. All right, and when we take the antiderivative of that, that is called integrating. So the only way that we know how to take the antiderivative of this is to go backwards in our head and undo the power rule for derivatives. So we would add 1 to our exponent, so that would give us an x to the 6th. And then we have to ask ourselves, 6 times what will give us that 1 out front? So we would have to put a 1/6 here. All right, now when we take the derivative, that's how you check an antiderivative. You take the derivative. 6 times 1/6 gives us the 1 out front, and 6 minus 1 gives us the 5. So that's how we go backwards in our head. Also, don't forget, on the end of every antiderivative, we put plus c. So the goal for today is to learn how to do that without going backwards in our head. We're going to learn the power rule for antiderivatives. Inside this box, we've kind of talked about it. So just read through that. That's all the fancy calculus notation. There's a couple properties that we want to remind ourselves. They're the same properties that we used for derivatives. The first one is, what do we do with a constant out front? The integral of a constant times a function. Remember, that k, that constant out in front, comes along for the ride, and you take the antiderivative of the function. So let's look at this example right here. We want to take the antiderivative of 5 cosine of x. So that constant out front, right here, that comes along for the ride. All right, and we take the antiderivative of the cosine of x. All right, so the 5 comes along for the ride. We know that the antiderivative of the cosine is sine of x, and then plus c on the end. All right, so just like derivatives, the number out in front comes along for the ride. Let's look at this example. All right, well, we know that this 5 out in front comes along for the ride. That's the same as 5 times the integral of the function x to the 5th dx. So 5 comes along for the ride. We know that the antiderivative of x to the 5th, we just did that, is 1/6 x to the 6th plus c. I'm going to make 5 a fraction. I'm going to put it over 1. And when I simplify that, my antiderivative is 5/6 x to the 6th plus c. All right, and to check an antiderivative, you take the derivative. So the derivative power rule, 6 over 1 times 5 over 6, the 6's cancel, and it gives us our 5. 6 minus 1 gives us our exponent of 5. So we did it correctly. The other property, it's the same for derivatives. It not only works for the sum of two functions, it works for the product of two functions, it works for the quotient of two functions. It just simply says this: if we want to take the integral of one function plus another function, if your function consists of two functions added together, you simply distribute that integral. You take the integral of the first function and you add it to the integral of the second function. So you take the antiderivative of the first function plus the antiderivative of the second function. All right? So, not too much to worry about there. Let's move on and learn the power rule. Okay, just like the power rule for derivatives, the power rule works for any polynomial term. All right, you need a coefficient. I'm just going to call it a. You need x, and you need an exponent. All right, the power rule works for any polynomial term. So that's what you see here. The antiderivative of u to the nth du. So again, this is just the notation telling you to take the antiderivative of u to the nth. Here's what we do. You do two things. You add 1 to your exponent, and you put the same number on the bottom. So there's two steps. You add 1 to the exponent and you put the same number on the bottom. There will always be a denominator before you simplify. All right, so it looks like this. Example number 1. To take the antiderivative of x to the 9th, the first thing we do is we add 1 to the exponent, so that gives us x to the 10th, and we put that same number on the bottom, x to the 10th over 10. Now you need to simplify. That's the same as 1 x to the 10th over 10. You need to pull out that fraction and write it as a coefficient. So you would write it as 1/10 x to the 10th plus c. The reason you want to simplify it and rewrite it and pull that coefficient out is so that you can check your work. Now check your work by taking the derivative. 10 times 1/10 gives us a 1 out front. 10 minus 1 gives us 9. So you use the power rule for antiderivatives to take the antiderivative to get from here to here, and then to check this work, you use the power rule for derivatives. It's a lot to keep straight in your head, going back and forth between both power rules. All right, let's go to the second example. All right, so again, the 5 comes along for the ride. So we're taking 5 times the integral of the function x to the -7th dx. The 5 comes along for the ride, and we use the power rule on x to the -7. So we add 1 to our exponent, so be careful. -7 plus 1 gives us -6. So we have 5x to the -6, and we put the same number on the bottom, plus c. Now, one thing to keep in mind, when you take the antiderivative, the notation, that big elongated s and the dx drop out. Okay, let's simplify it. Let's pull out the coefficient and get it out front. So it looks like this. -5/6 x to the -6 plus c. There's my antiderivative. To check your work, take the derivative. -6 times -5/6 gives me the +5. -6 minus 1 gives me the -7. Let's go to number 3. All right, we use the power rule on x to the 22nd. So we add 1 to the exponent, x to the 23rd, and we put the same number on the bottom, plus c. That's the same as a 1 out front, and you must rewrite it, simplify it, and get that coefficient out front. So 1/23rd, x to the 23rd plus c. Let's go to number 4. Number 4. All right. The 10 comes along for the ride. We're only going to take the antiderivative of x to the 4th. So, again, 10 comes along for the ride. For x to the 4th, the power rule tells us to add 1 to the exponent, so we get x to the 5th, and we put that same number on the bottom, plus c. Now, when we simplify, hey, 10 over 5 gives us 2x to the 5th plus c. Now check your work. Take the derivative. 5 times 2 gives us the 10. 5 minus 1 gives us the 4. That's it. That's the power rule for antiderivatives. Now we're going to learn a couple more antiderivatives, and these are just your flashcards. These are the ones that you just need to know. The first one is the one we all know and love, e. Well, the derivative of e to the x is itself e to the x, so guess what? The antiderivative of e to the x is e to the x plus c. It is itself. Yay! All right, now the next thing we're going to do is we're going to learn the antiderivative of an exponential function of any base. So let's first review derivatives. Differentiate means to take the derivative. So when we took the derivative of b to the x, remember, we rewrote the function again and we multiplied it by the natural log of the base. Let's practice that. Differentiate, again, means to take the derivative. So we just follow that formula. Y prime, we write the function again, 5 to the x, and we multiply it by the natural log of the base 5. That's it. You're done. All right, down here for number 2a, the derivative of x to the 11th, y prime is, we write the function again, 11 to the x, and we multiply it by the natural log of the base 11. So that was a review of how to take the derivative of an exponential function of any base other than e. Now, to take the antiderivative is the opposite of the derivative. So what is the opposite of multiplication? It's division. All right, so to take the antiderivative of an exponential function of b to the x, and that's right here, the antiderivative of b to the x, you rewrite the function and you divide it by the natural log of the base. You're just doing the opposite. So to take the antiderivative of 5 to the x dx, you rewrite the function and you divide it by the natural log of the base plus c. Remember, when you take the antiderivative, the big elongated s and the dx drop out. So there's your antiderivative. And we'll practice it again. To take the antiderivative of 11 to the x, exponential function base 11, you rewrite that function as is, and you divide it by the natural log of the base. And of course, don't forget plus c. Thanks, calculus!